These are images on expansion devices, unit 24. You'll find these images on this particular case right here, figure 24.39. These are temperature time graphs showing the set point, offset. Excuse me. These are going to be the figure 24.38, electronic expansion valve, EEV, feedback loop. These are going to be images, different types and styles of electronic expansion valves here. So if you have a mini split, if you have some of the newer technology, you're going to see this type of a EEV in that system. These are programmed, and they you have to have a board, you have to have feedback signal for these things to work. This is a typical TXV. Basically, you are looking at the superheat adjustment portion of the thermal expansion valve, which is located here. Notice it's a square shaft. It requires a service valve wrench, not a pair of pliers, not a crescent wrench. This is where you would make adjustments to the superheat spring on this type of TXV. It is not recommended you adjust these unless there is a problem. Usually when these valves are factory set, they last for many, many years and do not create any problems. This would be the sensing element for like the EEV. This is where you would actually get a feedback. You'd use something similar to this. In this particular case, this is figure 24.34. It's a thermistor used as a temperature sensor for the controller input. Okay, here we have a unique situation. Notice that we have magnets that are energized, and notice that you have a north pole, south pole, and you have this would be very similar to a situation for like an electric motor. And I believe this is probably tied into that stepper motor. I'm going to see if I can find the illustration in the textbook regarding this particular diagram. But looking at this diagram, this would be how a motor typically works, and it works off the repulsion type thing. This is found on figure 24.35, electromagnets which are placed around a permanent magnet rotor. Here we have a power head on a TXV. And this one here, notice that you got some different information here. It gives you the temperature range in Celsius as well as Fahrenheit. And then it has the instructions like MOP 15. This here is a Danfoss TXV. I believe I saw this illustration just a few seconds ago, and I can refer you to that in your textbook in unit 24. Notice that the power head is stainless steel. They work extremely well when they work. When they don't work, then we have problems. So this particular unit shows the let's see here. Okay, this will be the TXV. This will be figure 24.23 on page 588. This is going to be the TXV showing the maximum operating pressure, which is MOP of 15 PSI for the compressor protection. So MOP stands for maximum operating pressure. In this case, it's 15. This is a very important part of the TXV. You're going to find this on the liquid line inlet to the TXV. Notice this is a fine mesh screen. Typically, this will mate to a copper flare nut assembly here. These screens have been known to collect debris, such as copper shavings from the installation of new equipment. These have been known to collect dirt accumulation, situations where you take and braze equipment or make repairs to a to an air conditioning or refrigeration system, and you don't run nitrogen through. Typically, the properties of scaling, flaking, things like that end up in this mesh screen. And over a period of time, these strainers/screens on the inlet side of the TXV are going to plug up. And the indication you're going to get as a service technician, if you look at your gauge manifold set on the high side, you're going to show a restriction. And that's indeed what this is. So if you have a TXV that is not operating correctly, one of the first things you should always check is to remove the inlet screen. Chances are that's going to be your issue. Okay, here we have an interesting item here, something I haven't seen since my training days back in the 70s, when we utilized a lot of capillary tube metering devices. There was a device, if you look at this thing, it looks like a, it looks very similar to a hydraulic jack, which it kind of more or less is. And what happens is this. You're basically going to take and clean out the interior of the capillary tube, which is a very tiny opening, utilizing this these different sizes of internal tracers. These tracers are inserted into a specific capillary tube that is believed to be plugged up. And if it is plugged up, you're going to insert this little chaser type wire into the interior of the capillary. And then you're going to take this hydraulic jack and you are going to hook up the outside of this capillary tube to this hydraulic jack and pressurize it. The other end of the capillary, of course, has to be out of the refrigeration system. The theory behind this is you build up enough pressure, you are going to be able to take this chaser/wire piece and push it through the capillary tubing and clear it out. This is something I have not seen used in years and years and years. I'd be very curious to find out if anybody still has one of these. Okay, here we have another thermal expansion valve. Notice it's a brass body. And notice on the bottom of that, you have the adjustment, the superheat spring adjustment. As I said earlier, and I'm going to reiterate, it is not a good idea to adjust this thing in any way, shape, or form. The one thing I want to call your attention to, notice that you have a port here, you have a port here. Right over here is the external equalizer connection. That is a piece of 1/4 inch copper tubing, which is going to be sweated or flare nutted onto that fitting, and it is or a capillary tube depending on the brand, and it's going to be mounted to the outlet side of the evaporator coil. You're going to use an external equalizer when you have a significant pressure drop. So as an example, let's say the inlet and between the inlet and the outlet of a multi-circuited evaporator coil has a pressure drop of 5 psig. You would utilize this type of TXV in that particular situation because the pressure drop is significant enough that the valve is not going to operate correctly due to the pressure differential without this equalizer in place. Okay, here we have a situation. We're looking at the evaporator coil, the evaporator fan, liquid refrigerant line in, the metering device, which is located right over here. Okay, and we should be able to find the sensing bulb, hopefully mounted in a horizontal position on the line out. I don't see it here necessarily. I suspect this might be the equalizer line that I've got my cursor running to right here. Okay, here we have a refrigeration diagram, basically showing the compressor which pumps heat-laden refrigerant. It goes through the high side, in this case, the high-pressure vapor line, going through the condenser where it gives up the heat that was absorbed in the evaporator. As it gives up the heat, the high-pressure, high-temperature refrigerant vapor now becomes high-pressure, lower-temperature liquid, and the liquid refrigerant will collect here in the receiver. And in the receiver, then of course the refrigerant is drawn to the TXV, which is right here. And the evaporator, of course, absorbs the heat from the space or the food product. And then as this refrigerant goes in at a liquid, 75% liquid, 25% vapor, this refrigerant is going to boil off. As it boils off, after it goes through this metering device, in this case, the expansion device, the pressure drop is significant enough to allow for the refrigerant to take and boil off and absorb heat of the food product, or in this, or in the air conditioning mode, absorb heat from return air. Basically what happens is when this refrigerant boils off, the liquid eventually turns into low pressure vapor, and it of course leaves the evaporator coil where it goes down the suction line into the reciprocating compressor. The cycle starts all over again. Once again, I'm going to reemphasize that compressors are not designed to pump liquid under any circumstance. There's the external equalizer connection on this TXV. And in this particular TXV, notice that we don't have a place where we can adjust the superheat spring. Okay, here we have a situation where we have a TXV, which is mounted to a distributor. And on this distributor going into the evaporator coil, we probably have a minimum of 3 circuits. So basically 3 circuits in here, we have a significant pressure drop. We're going to employ the use of an external equalizer connection. Notice that it comes right off of the TXV and it goes to the outlet side or suction line as far as to provide this pressure equalization so that this valve can respond to changes in the load in the evaporator coil. Okay, we have a different situation. This is found on page 583 of your textbook under figure 24.14. Basically what happens here, the real pressures as they would appear in the system, the pressure drop across the expansion valve is not necessarily the head pressure versus the suction pressure. The pressure drop through the refrigeration distributor is one of the big pressure drops that has to be considered in order for this valve to work correctly. Refrigerant distributor between the expansion valve and the evaporator coil. So basically you got the distributor. Notice that you have different pressure drops, and because of that we need to have the external equalizer to basically compensate for all this pressure drops that are taking place in the evaporator coil. Now notice that the TXV thermal sensing bulb is mounted in a horizontal position. Depending on the size of the copper line, it is going to be, we typically look at the clock and we will say 10 o'clock, 2 o'clock, 4 o'clock, 5 o'clock, depending on what the size of the refrigerant suction line is. Always mount these things on a horizontal plane, not vertical. And more importantly, please use the copper straps. When you are mounting these bulbs, make sure the area between the bulb and the copper suction line is absolutely clean. Make sure you have a nice tight conductivity connection between the copper line and the sensing bulb. Okay, this is an interior picture showing the superheat spring inside. It's one of the balancing forces in order to make this valve operate correctly. And actually, there's a more detailed picture, which I believe we're going to come to in just a second. But this is going to be found on page 584, figure 24.16. This is the superheat spring. Okay, here's the diaphragm. Here's the bulb with the refrigerant inside. Basically, this is another operating force on the TXV. Okay, here we have an evaporator coil. Notice that we have a mixture of vapor and liquid. Remember, 75% liquids, 25% vapor. As it goes through, this temperature doesn't change much. The pressure has already been decreased because this is the metering device. And as we get towards the top, that refrigerant liquid should be boiling off, should be absorbing heat, and coming through this last loop, we should be just about completely vapor only. And of course, the compressor is designed once again to accept and pump refrigerant vapor, not liquid. So please pay attention to the refrigerant inside the tubing, and notice as it gets towards the top on the evaporator leaving side. Okay, here we have a chart that talks about the operation of this valve. I'd like to refer you to this, which I will find the page for in just one second. This is found on page 587 under figure 24.21. The cross-charge valve has a flatter temperature pressure curve. The pressurized after defrost or at the end of the cycle will have a tendency to close this valve and prevent liquid floodback problems. So basically, this valve is designed to prevent liquid coming back to the compressor, which we know will cause problems here. So this is a cross-charge showing you the operating characteristics of a cross-charge valve. Once again, we have this diaphragm, which contains a refrigerant or a gas, maybe the same type of refrigerants in the system, maybe not. Sensing bulb only contains a very small amount of liquid. In other words, most of this is inside of this capillary tube on this diaphragm is vapor. Okay, we have another illustration here, which I believe is found on page 588. The graph shows the pressure inside the valve when the sensing bulb is in a hot area. And basically, this is what happens. Notice that we have a pretty straight curve pattern that is showing the operation of this. Remember, this is one of the balancing forces on a thermal expansion valve. Okay, here we have another situation here. This is also found on 588, figure 24.24. The liquid can migrate to the valve body when the body becomes cooler than the bulb. When this happens, the valve body can be heated with warm cloth and the liquid will move back into the bulb. Okay, in this illustration, which is on page 589, a TXV under normal load condition. The valve is said to be in equilibrium. The needle is stationary. So remember, you have operating forces, the superheat spring, the evaporator back pressure, and the bulb pressure. And notice that this valve right now is in a what we call an equilibrium mode. It is not feeding necessarily much refrigerant at this point because the pressure from the bulb, the back pressure from the evaporator, and the spring are all in equilibrium at this point. Then again, you look at the temperature of the evaporator coil. It does not rise until we leave the last loop here. Now we have a little bit of a different situation here. And I believe this is found on, let's see, hold on one second. Okay, I believe this is found on page 591, and this would be figure 24.27, and basically showing you what happens with a medium temperature application here. So this is a medium temperature application down here at the bottom, and up here, this would be a, this is going to show the pressure drop and shows the thing in equilibrium. Notice that this pressure does not drop off very much from, or I should say, yeah, the pressure does not drop off very much from here until it gets all the way to the outlet side of the evaporator coil. Same thing holds true down here. Notice that the temperature does not drop off very much until you get to the end of the evaporator coil and the going towards the suction line. So basically, medium temperature application, showing what the bulb is going to do at this condition. So this valve will be at equilibrium. If you look at the writing here, and the bulb pressure is 25.9 psig. The outlet of the evaporator is 29.5 degrees Fahrenheit. So basically, the operating forces are in equilibrium at this point. Okay, here we have another picture right here. And this one is, I believe this is found on page 592, 24.28, shows the correct method of connecting the external equalizer line. Notice that the equalizer line is always on the outlet side of the evaporator. You do not want to mount it close to the evaporator. You want to mount it on the suction line so that we can fully detect and compensate for the pressure differential from the pressure going in versus the pressure going out. Notice in this case here, it's medium temperature application. R134A is the refrigerant of choice in this case. Okay, in this situation here, again, we have a medium, we have the medium temperature application. And notice in this particular case, this is figure 24.29. When the equalizer line is connected before the sensing bulb, a small leak in the internal parts, the valve will stimulate a flooded evaporator. So it is absolutely critical that this equalizer line is mounted in the correct position. Right here is not a good position because basically we are not sensing the true superheated pressure refrigerant, which should be in a vapor state. We still might have a little bit of liquid here. Basically what's going to happen, we're going to cause a floodback situation with the refrigerant leaving the evaporator going back to the compressor. Okay, here we have a board. It's an electronic board which is found on page 595. This is a solid state stepper motor controller board. So if you're utilizing an EEV, you have to have a board and then you have to have inputs. Notice that you're going to have your 24-volt connection. You're going to have temperature sensors tied in here. You'll have a fuse connection as well. You have a bunch of wiring that comes into play here in order for this thing to operate correctly. and you basically have a set point potentiometer. Typically, you're not going to adjust these out in the field. They're adjusted from the factory. Basically, they either work or they don't. Check inputs and you check outputs. And if the valve does not operate correctly, obviously, you're going to have to change it. Okay, this is an illustration showing the stepper motor in operation. And I believe you'll find this on page 596. It's a digital linear actuator. So when we say linear, basically, we are not having abrupt openings. Basically, it is a steady, gradual incline to open this valve. And typically, we're utilizing a pulse signal to open this thing in steps. Depending on the EEV, it could be up to 150 steps to fully open the valve or close it. The reason why this is done that way to accurately control superheat on the evaporator coil. You will find this utilized in all the mini splits and a lot of the later model evaporator coils for refrigeration in stores, as well as in super high efficiency evaporator coils for residential air conditioning applications. Here we have the motor showing the wiring diagram. Notice they use Q terminals, Q1, 2, 3, and 4. And basically they are utilizing what appears to be a transformer at Q6. Let me verify that for you. Basically, yeah, this is going to be multiple transistors that make up the stepper motor. These are transistors in the stepper motor operation. Okay, here you have a diagram showing the actual temperature, the set point, the offset, and by utilizing this diagram, you can kind of tell the temperature time shows is how far, what the offset or error is on this particular unit. This is an extremely accurate device, the EEV or electronic expansion valve, and because it uses linear motion in order to gradually open, this thing is a very precision instrument in the control of superheat in the evaporator coil. Now you take a look at this diagram here. You have a little bit of a different situation here. Instead of the lines being perfectly horizontal, now we have a situation, this could be found on page 598 of your book, figure 24.40. The temperature time graph shows an integral controller showing set point, offset, and reset. Excuse me. Now we have another situation on 598, figure 24.41, and the temperature time graph of this derivative or differential controller showing the slopes or rates of change. Notice it's not linear, it goes up and it goes down, goes up and goes down, depending on how we're trying to control this. Now here we have an automatic expansion valve. With an automatic expansion valve, these are designed to work off of the evaporator pressure. You're going to set an evaporator pressure looking at a, let's say that you want a constant load situation. We want this valve to feed at a constant rate. So let's say we have a constant heat load in the evaporator, such as a box with chill water as an example to cool a product. Basically, you would use an automatic expansion valve. You're going to adjust the spring pressure with this set screw. You're going to have a gauge manifold set, and you're going to set the pressure that you want it to maintain under all conditions. In other words, this valve doesn't open close. It maintains a constant pressure inside the evaporator. So we have the liquid refrigerant coming in, and because of the spring set screw, this is going to feed liquid and vapor out at a constant pressure setting only. Now in this situation here, I believe this is going to be on page 599. Basically, if you look at this illustration here, this will be the top illustration, shows the automatic expansion valve under varying load condition. The valve responds in reverse to the load change. Normal operating condition, the letter B down below, which we'll get to. So we'll show you the various positions here of this valve as it opens and closes. Notice that the temperature range, except for the last loop, is constant. Notice the temperature coming in is constant. Notice that the pressure going out is 29 psig. Notice that the pressure coming in is 29. So what we are doing is maintaining 29 psig. And if you look it up on your pressure temperature chart, that should give you the corresponding saturation temperature. So basically we have air going in at 50 degrees and we have 33 degree coil. Okay, in this situation here, a little bit different. Notice that the suction line to the compressor is at 33 degrees. Notice that the pressure down here is 29 psig, 29 psig again. And basically a slight amount of liquid in this particular case is leaving the evaporator and heading back towards the compressor. And it can or cannot cause a lot of problems with this illustration here. So we need to be concerned basically if we are sending liquid back. So it's very important that the pressure setting of the of this AXV is set to prevent the refrigerant from heading back to the compressor as liquid. So it's important you consult the PT chart to make sure the corresponding saturation temperature, the pressure that you set on this valve is correct. Okay, this would be the last one. If you look at down below, well, actually the second one right here, notice that we are at 30 psig. Notice that the temperature, we start out at 33, we end up at 45, leaving this particular unit. And basically, we don't see any liquid heading back in this illustration here, okay? So basically, when the load goes up, the valve closes down and starts to starve. So basically, if you look at this evaporator coil, this is an example of a partially starved evaporator coil. When we say it's starved, that means it doesn't have enough liquid refrigerant coming in to boil off and absorb the amount of heat that is needed. This would be a high load situation. Okay, this is an example where a guy hooks up a garden hose, 25 feet of garden hose. He's got 100 psig. Now look what happens. This is kind of interesting. At 25 feet, and I'm going to assume this is either 1/2 inch or 5/8 ID. Notice that we have 75 psig, 100 at the hose tap and 75 over here. Now, if we increase the length of the hose to 200 feet, we still have 100 psig. Look what happens to our pressure 200 feet away. Significant impact here. So depending on the length of the hose, the less water pressure is going to show up. Capillary tubes function in the same manner. So basically the length of the tube, the ID of the tube, the internal diameter of the tube is going to determine the actual pressure. Okay. On domestic appliances and some small air conditioning systems, you will find a strainer dryer. This is found on page 601. Liquid from the condenser, then you got the condenser, capillary tube, and the evaporator. So this is your metering device, and this is the strainer dryer. These things can and do plug up. I will tell you that. These can only be sweated in. You have to take in heat, protect these from excessive heat when you are brazing in a new one, because the molecular sleeve inside here will get contaminated and cause problems with the refrigerant flow. Also remember, this is a strainer. These can plug up. How do you check for a strainer blockage on something like this? The best way I know how, without hooking up gauges, is to do a temperature check. If you have a temperature check between the inlet and the outlet side of this strainer slash dryer, you're going to be able to tell if we are passing refrigerant through or if it's stopping right here at this point. Okay, here we have another TXV. Interesting to see what the book has to say about this particular one right there. Give me a second while I find the illustration. Unfortunately, these pictures, instead of being in a chronological order, has a tendency to be spread depending on the subject matter that they're trying to cover. So bear with me. Okay, this particular valve, the only thing I want to call your attention to, you have a flare nut connection right here, and you have a flare nut connection here. Notice that you have a set screw right here. I'm still attempting to find out which illustration this applies to, because it's rather important that I give you the correct information of this particular type of TXV. I can't honestly say that you're going to see this very often. Okay, this is found on page 585 of your textbook, and this will be the letter B. And basically what is happening here, adjustment stems, some of them are, so you can adjust the superheat spring on this particular TXV with a slotted screwdriver instead of utilizing the square head on other valves. Okay, here we have an example of a refrigerator being controlled, in this case by a capillary tube as your metering device. Notice that the capillary tube is basically connected to the suction line going to the compressor. There's a reason for this. We want to increase the efficiency of this refrigerator, and we want to ensure by having heat, which is on the outside of this capillary tube, is going to take and pass that heat over to the suction line to ensure that no liquid refrigerant heads back to the compressor where it can damage it. So typically on most small domestic refrigeration systems, you will have a capillary tube which is attached to the suction line in order to increase the efficiency of this unit, but more importantly, help prevent liquid refrigerant from heading back into your compressor. And you're going to find this. Notice that they're using R404 alpha. This is on page 603 of your workbook. This is checking the superheat before the suction heat exchanger. So basically, the capillary tube acts as a heat exchanger to the suction line. Notice that the capillary tube is mounted or soldered on there. You cannot remove it. And basically, you have your strainer dryer where the liquid comes in and cleans out anything that is circulating. And of course, as this capillary is attached to the suction line, basically what's going to happen is you're going to create a significant pressure drop in order to feed 75% liquid, 25% vapor into this evaporator coil, and of course end up back. Now, if you notice with R404A, the 16.7 psig, the evaporator is boiling at -20 degrees. That's very chilly. Space temperature is 0 box in this case. So this is going to be a freezer application utilizing 404 alpha. Okay, this shows the breakdown of a TXV, how these things are constructed. A TXV typically has all these different parts. Now, I will tell you in the field, you as a service technician is not going to take the time to take and swap out parts. If a TXV has the tendency to go bad, which they very seldom, but they occasionally do go bad, you will just replace the entire thermal expansion valve. You will not try taking it apart, as this diagram clearly shows it can be. We just take and replace the whole TXV. when it goes bad. It's a precision instrument. This exploded diagram is found on page 580, and it shows the TXV with all the parts, such as the diaphragm assembly, the push rods, external equalizer connection. Here's the seat, the pin carrier, superheat spring, spring guide, the bottom cap. Here's your superheat adjustment spring, and then a protective cap. Okay, here we have R134A in this diagram. And the first thing I want to call your attention to, looking at that evaporator, looking at the pressure going into the evaporator, it appears to be a constant temperature of 20 psig. We're going from 180 to 20 psig through a capillary tube. And notice that the temperature drops off dramatically as a result. So when it drops off as a result, by looking at this diagram here, basically utilizing this capillary tube, this is the result that we would expect to see. So what is this telling us here by looking at this diagram? By the way, you can find this diagram at the top of the page on page 601 of your textbook. This is a typical operating condition for a medium temperature application. The strainer dryer protects the capillary tube from circulating particles. So basically, you have a strainer which is down here and prevents those particles from getting in here, plugging up the capillary tube. Go from 180 to 20 psig. We're at 21 degrees. And basically the refrigerant, notice, maintains a 21 degree temperature until we get up to the last loop. And then the temperature and pressure rise at this point. The pressure does not rise significantly. However, the temperature does, because the refrigerant basically has boiled off and changed to vapor. Okay, here we have a situation showing a cross section of the TXV. It basically shows the components. Of course, here's your power head assembly with the thermal bulb, and this shows the equalizing areas. Here's where that strainer basket is going to be mounted on the liquid side coming into this TXV. And with this type of TXV, these strainers have been known to get full of junk. Do they need to be cleaned? Absolutely. But the thing I'm going to ask the question is, what's that stuff doing in the first place? Was the service tech or installation crew sloppy when they installed this TXV? Well, you need to do some research. If that thing is plugged up, there must be a reason for it. One of the things that I've seen in the past on refrigeration, when they switch refrigerants, such as getting rid of R12, so basically if we have refrigerant changed from one type to another, and if we switch the oil in the compressor from alkylbenzene as an example to POE, POE, by the way, is a very good solvent cleaner. It cleans anything and everything. And guess where the contamination ends up? Right here on the strainer basket on the inlet side of this TXV. Does it happen? Absolutely. This illustration can be found on page 594 under figure 24.30, and it shows you how this valve works. So this is your equalizing forces at work inside this TXV. This shows the face of the needle. This shows the evaporator inlet. The refrigerant flows through here, and notice that because this thing is not completely closed, we are allowing a pressure drop to take place, and we are actually sending 75% liquid, about 25% vapor into the evaporator coil, so it can boil off. Okay, here we have an EEV, electronic expansion valve. We utilize a controller to operate this valve, and we have a feedback loop. And basically what happens is the sensor is an input which feeds the controller. The controller actually operates this stepper motor, which either opens and closes the valve. Here we have another diagram showing the TXV. And notice that it appears to have like a double power head assembly. I want to call your attention to the fact it looks like a double power head assembly. You can see what the book has to say about this. This illustration is going to be found on page 594. It's a pressure limiting expansion valve. When the pressure is high in the evaporator during a hot pull down, the valve will override and the thermostatic element with a pressure element and throttle the refrigerant. Here we have an illustration of the various aspects of this TXV here. Notice that we have 3 diagrams here. This is also in your textbook. Shows you what happens. I believe this is a, not sure if this is a medium temperature application or not, but we will find out. Anyways, in the interest of time, I'm just going to show you what, if you take a look at the what happens with this valve as it's opening or closing. Notice what happens to your pressure temperatures. In this case, on this top illustration here, notice what happens here with the valve when it opens up. Notice down here, the liquid going in. It looks like we appear to be having some flash gas taking place. In other words, refrigerant which is boiling off prematurely. It's not supposed to do that, but it does. And by the way, you will find these diagrams on page 586 under 24.19. All components work to hold the needle and seat in the correct position to maintain stable operation with the correct superheat. A, the top illustration is in equilibrium, B is the valve opening, and C is the valve closing. Equilibrium, opening, closing. So notice how the pressure temperatures change in this respect. Okay, here we have another illustration of a TXV. Notice that we have warm liquid going into the liquid inlet side of the TXV. And of course, right there at the inlet, that's where that screen is going to be located, folks. If you ever have a situation that appears to be a restriction, let me suggest to you, if you have a thermal expansion valve, that you have a screen which is plugged up. It will show up as a restriction. And the only way you're going to be able to fix this is you have to take the refrigerant out, and you basically have to take and pull this valve apart, take out that screen, clean it. Now, the thing I'm always going to suggest when you do that, find out why it plugged up. There's a reason why those things plug up. Usually it's sloppy workmanship, sloppy service procedure, something to that effect. But it's very, very important when you are working on a TXV, you take and practice the right methods for servicing these valves, the right methods for replacing the valve, and you want to check to make sure that this valve is doesn't have any issues that can cause problems. So let's see, I'm trying to find a picture of this, and I don't think I have found it just yet. Oh, I have found it. It's on page 579. and this will show up as 24.3 down towards the bottom of the page. The expansion device has a dramatic temperature change from one side to the other. So basically, stop share. I'm going to finish this lecture shortly. I have to step away from the screen. Okay, we're looking at this illustration here of a thermal expansion valve. You're going to find this picture again on page 579, figure 24.3. The expansion device has a dramatic temperature change from one side to the other. And basically, notice that we have the, look at the temperature of the refrigerant. Its saturation temperature is 110 degrees, 180 psi-G. Going into this thing, needless to say, this valve is wide open because we are feeding lots of refrigerant in the evaporator. Now, the important thing, once again, even though this is 134A, the refrigerant leaving is a low pressure gas going back to the compressor. And basically, we have a dramatic pressure drop. And of course, the absence of heat, in this case is cold, low pressure refrigerant leaving the valve as a liquid, which is 75% in volume and about 25% or less in flash gas. And when we talk about flash gas, the term I'm trying to tell you is this is some of the refrigerant that is prematurely boiled off prior to absorbing the heat out of the evaporator coil. And so in this case, this flash gas pressure is about 3 psi-G, according to this illustration. Okay, here we have a little bit of a different situation here. If we look at this layout of this TXV, this is basically giving us some information showing what the spring pressure is, the balance, and it shows the actual temperature characteristics of this valve. And let's see if I can find this in your book so that we can, this will be on page 582, and this would be figure 24.12. The diaphragm in the expansion valve is a thin membrane that has a certain amount of flexibility. It's made of a hard metal such as stainless steel. So we're trying to tell you here, this is not a rubber or some product can wear out. This is a long-lasting product that should give years and years of good service. And of course, this shows the operation of this valve on the pressure and temperature being sensed here, the pressure being exerted on this diaphragm. In this case here, we are in a position where we're not feeding that much. So the suction bulb temperature, the suction temperature at the bulb is 37 degrees. The saturated refrigerant temperature is equivalent to the evaporator outlet of 27 psi-G, which is 28 degrees Fahrenheit. So we basically have in this illustration 9 degrees of superheat, which is good. Superheat is extremely important in a refrigeration air conditioning system. The higher the superheat, the less chance we have of sending liquid back to the compressor and destroying it. So superheat, you must pay attention to it. When you are charging an air conditioning system, refrigeration system, superheat is a critical factor. Okay, in this illustration here, we have another TXV. This is something that you would just literally pull out of the box if you are putting in. Notice that the connection portions, this is found on figure 24.7. And basically, notice that our connection points are flare in this case. Here's the external equalizer connection. Here's the liquid inlet connection. Notice that right here we have a gasket. Inside here, this cone removes out, and your strainer is located right here. Don't forget, the strainers can and do get plugged up. Do not condemn a TXV because it has a plugged strainer. This strainer is designed to trap particles, dirt, etc. And occasionally, due to poor refrigeration, air conditioning service practices, these things have been known to plug up. The good news is if you take the refrigerant out, pump it down, isolate it, you can remove the strainer, clean it, and put it back to good use, and put it back together, and you should be good to go. This is the superheat adjustment spring, and this is the set place where you would use that wrench with the square head to change the tension ratio of this valve. I do not recommend messing with these, changing the superheat setting. These are factory set for a certain temperature. Leave them alone. If they're not operating correctly, probably the chances are you got a problem with the power head, or you have a problem right here with this strainer inside the liquid line. In this case here, we have another valve. Notice that this particular one is located down in on page 581, and this is the letter B. Okay, with this particular one, remote sensing elements can be replaced. Okay, so what we're saying, what is repairable is this power head assembly. These have been known to go bad. The good news is these are field replaceable. You don't have to take it and sweat this valve and tear everything out. You can, with certain valves, such as this one here, replace the power head assembly and put a new one in. Make sure it matches the refrigerant that it's going to be sensing, that kind of thing. Make sure it's from the original equipment manufacturer. As long as you just check this out, this is something that is easily replaced out in the field. Okay, here we have a diagram showing basically the thermal expansion valve in various situations here. Notice that the pressure on this is R134A refrigerant, and in these two diagrams, we have the letter A and the letter B, and I believe we can find these on, speaking for the page. Okay, I believe this is on page 590, figure 24.26. And basically what happens is when we add food to the evaporator coil, look what happens to the temperature here. The temperature raises. Notice, look what happens to the temperature on the return bends on this evaporator. It goes up to 25 degrees. We actually leave the evaporator coil in a low pressure vapor state at 35 degrees Fahrenheit. Now we're at 40. And then, of course, then we go back to the compressor as a vapor only, which is good. Now, as the load decreases, look what happens to this temperature. It drops down to 18 degrees because the product has been releasing the heat content to the refrigerant. Refrigerant, of course, absorbs this. And then as the refrigerant absorbs this, it boils off, changes from a low pressure atomized liquid vapor mixture, 75-25%. And notice at the last point around the evaporator, we're at we should be at a vapor going here. Notice that we're at 22 psig because the temperature has dropped because the heat product has given up some of its heat. And so you can see clearly the difference of what's going on here. Here we have the bulb pressure at 35.1. Here we had the bulb pressure 22 psig. Quite a bit of difference because the spring is overcoming. In this case, the bulb is overcoming because the superheat is so high. More internals to this TXV. Basically shows how this thing works. Notice that you have the different pressures or the balancing ports. Basically, you have F1, which is the bulb pressure, F2, which is the evaporator pressure, F3, which is the spring pressure. These three pressures have to operate in conjunction for this valve to function properly. If they're out of sync, the valve is not going to work. It's as simple as that. Or it's going to remain closed, or it's going to go wide open. If it stays wide open for too long, you risk sending liquid back to the evaporator coil. And this, of course, is a cross section showing how the refrigerant is fed through. Do these needles and seats wear out? Yes, they do over time, but that's over a period of many years of hard constant use. They generally last a long, long time. Here we have a PT chart, and basically we're showing the thermal expansion valve capacity in tons. When you purchase a thermal expansion valve, it will be rated for the tonnage that it can handle. This chart, by the way, can be found on page 584, 24.15. It shows the capacity of the valve at different pressure drops. So you have the valve types over here on the left, and basically shows the pressure drops based on the evaporator temperature, 40 degrees, 20 degrees at 0. So you're going to make a selection based on using this chart, okay? Notice that the capacity of tonnage, this is critical. When you are putting in a TXV on refrigeration systems, you must pay attention to this, because you put the wrong size valve in here, it's not going to operate correctly. It's going to overfeed. You might send liquid back to the compressor. And of course, we know what's going to happen when that happens. Okay, this is something I deal with all the time in the air conditioning business. This is an example of a piston type metering device, very common in air conditioning applications. Instead of a TXV, we are using a fixed bore. The internal of that hole is basically going to determine the capacity of the refrigerant flow. Notice that you have a Teflon O-ring right here. These rings have been known to break and wear out. The other thing I've seen happen out in the field is these holes can get plugged up. So it's extremely important that you have a filter dryer to trap any junk. If this thing gets plugged up, you're going to have a restriction and it will not feed refrigerant. You'll have the symptom of a starved coil. The good news is these are easily field replaceable. The critical thing you need to look at is this number right here. The orifice size is critical depending on the tonnage of the unit. This is the number you need to pay attention to. You have to insert it. There's only one way you can insert this. If you install this the wrong way, you're going to have issues with this. Please make sure when you replace this that the bore is clean. Make sure that it's installed in the position that'll check to this position on the gasket. If it's installed the other way, you will have problems with this. Here we have a receiver, and notice that we have a service valve over here with a flare nut connection, a port where we can hook up our gauge manifold, and the same holds true here on the other side. So here's a bolting mechanism for bolting this receiver to the chassis of the refrigeration system. And of course, we have liquid refrigerant is stored here. Depending on the load on the evaporator coil is going to determine how much liquid refrigerant is inside here that is needed at a given time. Okay, here we have another example of a TXV. This one's kind of interesting because if you look towards the top, instead of a bulb, you notice it has a knurled nut assembly. This is a little bit different. Basically what it's designed to do. This is found on page 599 of your textbook. This is an automatic expansion valve. The valve resembles a TXV, but it does not have a bulb for sensing temperature at the suction end of the evaporator. So this would be an example of a sweat type AXV. You are going to set the pressure saturation temperature right here with this knurled nut. And once you set it, you forget it. Notice that this thing is clearly stamped inlet. Liquid goes in here, liquid vapor leaves here. Please make sure when you install these, you look at where you're supposed to hook these things up. If these have the same, if the piping is the same on this side as the outside, make sure you look at the valve body and make sure you install this correctly. I have seen situations where people have installed these wrong and I've had to come back and fix them. Here's another example of an AXV. Of course, here we have the TXV with the sensing bulb here. And down here, we have the capillary tube with a bullet dryer. Notice that we have access to the liquid connection through a Schrader valve here. So we have our liquid going in here through the strainer dryer, and then the cap tube hooks on this end. And basically, this is the way it works. Okay, this is what you will find on a lot of Evaporator coils on air conditioning applications. Notice that we have, instead of sweat fittings, we have the ability to take this valve off of the evaporator coil utilizing wrenches. These have to be specific to the evaporator coil it was designed. They're fairly easy to work on. What I love about this particular valve arrangement is they are field replaceable. You have to pull the refrigerant charge out, not a big deal. After you pull the refrigerant charge out, you can take these things out and you can replace them. You're going to find this based on page 581. And basically, this particular valve is field replaceable. Okay, have to order this from the distributor. Of course, you still have your power head assembly. Here you have your equalizer connection. Typically, this is going to be the only brazed or soldered connection going to the outlet side of the evaporator. This connection, there is a O-ring, a Teflon O-ring that mounts in here. There's a Teflon O-ring that mounts here. When you change these valves out, you must change out the Teflon rings without fail every time. I carry a bunch of those in my truck because occasionally those things do leak. Here we have a flange mount version of a TXV. I've seen a lot of these in commercial applications. When I was in the US Navy, this is the type of valve that we would normally install on a refrigeration or an air conditioning system. The reason being, with the flange connections, we did not have to drag a torch down at a crazy place in order to gain access to it. The flange connection works very well as long as these bolts are tightened up correctly, as long as the gaskets are in good operating order. Other parts of the valve are still the same. Power head assembly, superheat spring adjustment down here, the bulb, all the stuff remains the same. And depending on the evaporator size, you may have to have an internal or external. Typically, on a large pressure drop on an evaporator coil, you must use an external equalizer connection. Okay, now this is important. Anytime you install an evaporator coil on a customer's house or in a refrigeration system, you need to look at the spec sheet. They will tell you where to mount the bulb. In some cases, the bulb is mounted at the factory. You don't have to do a thing. Other cases, the bulb is loose and you have to mount it. This is what is critical here. Where this bulb is located, depending on the copper line size. Notice that the bulb is never on the bottom because that's where most of the liquid is going to accumulate. That is going to create problems with the sensing of the true state of the refrigerant inside of this suction line. So we typically will visualize a clock movement right here. And by visualizing the clock movement, here's what's going to happen. Basically, we are going to do this. With this clock movement in place, we are going to take and mount it, in this case, 5 o'clock, 7 o'clock. Notice that we have a copper or a brass type clamp, and this area is really clean, and we also insulate this area where the bulb goes through. Notice that you got 2 clamps here. Notice that you have a single clamp here. Notice how this thing is clamped. Basically, external bulbs on small suction lines less than 3/4 inch, external bulbs on large suction line over 7/8. So typically on the smaller ones, you can get away with mounting towards the top, but you never mount this in the bottom. It's either going to be 7 o'clock or 5 o'clock, or typically 1 or 2 o'clock. You can mount it directly on top. It doesn't really matter. But if you look at these illustrations, the bulb is always mounted in a horizontal manner. Here we have a capillary tube that you purchase from the distributor. It'll come like 5 feet, 6 feet, and basically the internal diameter of the tubing is going to determine, the refrigerant flow, basically the refrigerant capacity, and you need to know the ID versus the length of the capillary tubing. Last but not least, here we have a, shows what a capillary tube looks like with 134A. Notice that you have a pressure drop right here, 170 PSIG. And look at, by having 20 inches here, our pressure drops down to 20 PSIG. Here we have the same illustration at 170 PSIG, just like before. The only thing we have done is change the length. Notice that the pressure is still 20 degrees PSIG. Basically 1.5 pounds per minute here. And basically this will give you an illustration of what type of capillary tubing you have to use, the length of it, the ID. These are the things you have to keep in mind when selecting and replacing capillary tubing as a metering device. So please be aware of that. And I believe that is it for this lecture environment. You can find this illustration on page 600 under figure 24-46. And basically this shows what happens here.